Hello.
Hello, sir.
Hello. Yeah, hi. Sorry, I had to go to the team service for some reason. So I was late by 15 minutes. So yeah. So before I start the class, the usual practice. So tell me any doubts, any questions that you have. Did you guys attend the this tutorial?
Yes, sir.
Yes, sir.
Did it
Yes,
help
sir.
to clarify some of the doubts?
Yes, sir. For some problems, but some like discussions are still left. So
Okay.
because we have only an hour for the tutorial, and then
Yeah. So if you want more, then also we can arrange more for that.
sure, sir. I mean,
Yeah.
I think if it is required, we might, because everything that was discussed was quite clear.
Okay.
But there were a few problems that we left that we
Right.
had to discuss.
Okay,
That
so
was
let
good.
so of course, I mean, I would need a one more slot. That's one thing, right? And and I will talk to the TAs also, and accordingly, we can fix up another slot for. I mean, add the addition to that whatever 7 to 8 slot on Friday that we have. Yeah. So so should we start today's new topic, or do you guys want to discuss something that was done till now?
Sir, in the assignment problems, were we supposed to provide these proofs of correctness for every problem?
See, again, these are like the kind of like typical math thing that you write, right? If the proofs of correctness are obvious, then you don't need to write it. If they are not, then you have to write it, right? I mean, it's
Yes,
like
yes.
a standard thing when you write a proof of a theorem. Some statements can be obvious, and you kind of skip that. Some statements are not obvious, and then you write it, right? So the main idea is that they have to have a formal proof. Now, that formal proof, how much of it you should write, how much of it is kind of obvious, that's up to you.
Yes, it's about that thing. So
Yeah.
So after
so if the TAs have cut marks for something, okay, and you think that is obvious, then you can ask them that. I mean, you can have a discussion with them, okay, and you have a better understanding of that. So it is not necessary. I'm not asking anybody to write a proof from the first principle kind of stuff, right? But a formal proof should be there. Now, of course, you can write a lot of step jumps, or some of the things can be obvious. Now, yeah, there are these kind of things like what is considered obvious, what is not considered obvious, and so on. But that I am sure you will get to. I mean, try to solve more and more assignments, and once you have that discussion, you will have a better understanding of what is it that yeah. So, like for example, what we'll be doing now, okay, from now on, are things which are not obvious. Let us tell you that. But the proofs of theorems will not be obvious, or proofs of algorithms will not be obvious. So in that case, a formal proof will be needed. Yeah.
Hello.
Sir, are
Yeah,
we
yeah.
still going to have the
Sorry.
Aniket, go ahead.
Okay, thank you. Sir, I was asking, are we still going to have the best 5 out of 7?
Yeah, those things are fine.
Evaluation
Yeah.
in
Don't
terms of
worry
the
about
assignments
that.
and quizzes?
Yes. See, I mean, I have no
Okay.
intention of giving you less marks in your assignment and quizzes. Okay. I mean, the assignment and quizzes are all there to help you prepare. Okay. So basic simple thing is that if you do your assignments and quizzes, then you will do well in your midsem and endsem also. So by the way, I will put up another assignment today, which will be due in 1 week's time. That will be before your midsem. And
Okay.
yeah. So yeah. So I will try to do the best I can to give you more marks in your assignment and quizzes. Okay, so that's not a problem. But the main thing is that you should try to solve them, and that will help you too for your midterm exam. Of course, midterm exam carries most of the percentage.
Sorry, I joined late. Could you please, tell me what you are saying right now?
No, we are not discussing anything non-trivial. We are just asking whether there are any questions or not. I have not started on a new topic yet.
Oh, so no, you are saying something about assignments?
No, there were questions about whether we will take the best 5 out of whatever number of assignments. So yeah, so thing is that we will do that. We will try to ensure that we will, if there are 4 assignments, then I will take the best 3 out of 4. If there are 5 assignments, I'll take best 4 out of 5, kind of stuff like that.
So, and another thing, could you, do we have to like give the proofs of correctness for everything that we write?
Yeah, I just now told it to your friends. So it is exactly like how you write a proof of a theorem. You are comfortable writing proof of a theorem,
Yes,
right?
sir.
You don't write every possible step, right? Some of the steps are obvious to you.
Yes,
right?
sir.
What we kind of call in colloquially jumping steps, right?
Yes,
Step
sir.
jump. So here also is exactly that.
Okay.
Important thing to note is that the theorem or the algorithm must have a formal proof. Now, whether you need to write the formal proof in how much detail, that depends upon how obvious is that. Okay. Now, if you think that what you have written is an obvious statement, then don't write that.
Yes, sir.
Okay. But if it is not an obvious statement, you might have missed some delicate point, then of course we will be maybe cutting marks. There are some delicate points out there which you missed, really, which I am not 100% convinced that you understand literally. Okay, so that's basically, this is exactly like that. It's a proof of a theorem or proof of a mathematical statement. Now, how much details you have to give, that is up to this stuff, right? So when you write a proof of a theorem, there are certain facts or lemmas or something will not even prove it. Like, yeah, this is obvious. Exactly like that.
Sir,
Yeah.
sir, will it be possible for you to send us some model solution kind of thing for at least like 2 or 3 problems so that we
Okay.
can understand, exactly how should we write a solution?
Okay, sure. I will do that. I will do that.
Thank you, sir.
Sir,
Yeah.
so could you also just tell us about the modality of the midterms exam?
See, midterm exam, as far as I understand, it will be online, right?
Right.
And it will be on Google Classroom only. Okay.
Okay.
It will be a 3-hour program, 3-hour class, not class, 3-hour exam. Okay. You will have the this question paper will be available to you in the beginning of this thing, and you are supposed to write it up, scan it up, and upload it in the Google Classroom. Okay. So more details like how you should write it up and all those things, those we can talk about it later.
Okay. Okay. And there is no accompanying Viva or something like that?
There is no accompanying Viva. But again, as one thing that I should kind of point out, and this is something that we are doing it even in the assignment, the first quiz and the second one and all. Okay. That note that if any 2 of you, okay, we find a big chunk meaning a long enough sentence copied from each other. Okay, and there is no question, if there is a big enough non-trivial sentence that is identical in 2 papers, then I will assume that you 2 have copied it. There is no way, you are a student of probability, you should realize that probability of that happening is very low, right? That you have not copied and you still got the same long sentence there. Now, if that is the case, then you both of you get 0 in the whole paper. I'm not going to have any discussion about I have just looked at the second problem only. I have just I have done all the other problems by myself. No, I'm not even listening to any of it. Okay. So for your point of view, if you don't cheat, if you don't look at the internet, If you don't take and you sit down in your home, work out your these quizzes for 3 hours, I can bet you will be perfectly fine, and you will do well also if you just do your standard quizzes and problem sets and following the courses. Okay, so my exams are not very hard ever, but since particularly because it's the online setting, okay, I have no reason to take your Viva or any such things. Okay, it is just, I would think of it as like it is almost like an offline exam, where you come to the exam, you get the paper, you solve it, and that's it, and I correct it. And that the reason you have Viva and all is just because people don't believe that you guys will not be cheating. Okay, and I also I have the experience, so I can, of course, I know what happens. But this is my solution to it. Okay, if you cheat, you are under a risk of getting 0 in the exam. You might be lucky, and I might not be able to catch you. That's fine. Okay. So there will be no such things about Viva or any such things, and I would expect you guys are honest about it. Is this clear?
Yes, sir.
Yes.
Yes. So, yeah. By the way,
marks,
yeah. Sorry. Go ahead.
sir, how much marks will be allotted to midterm?
I think 30%. Yeah, 30% of the whole final thing will be in midterm. The standard, I think, 30% for the midterm, 50% for end sem, and 20 for internal assignments and quizzes. Yeah. Okay. Anything else?
Sir, I had 2 questions.
Yeah, go ahead.
So the first is about the 2n coin problem,
All right.
and the second is a new problem. Sir, should we discuss this to here right now?
The 2n coin problem, I would prefer if you discuss it with the TS. Okay, because it was there and the problem in the assignment, right?
Yes.
Okay, and
The second one is also a question. It's
okay, so maybe I can even the 2n coin problem. I mean, has it been discussed in the tutorial?
no, sir.
No.
Sir, it is said, Omkar sir said ki the next tutorial will begin with the discussion.
Okay, fine. I think I will leave it to be there. Okay. I mean, let it be discussed in the tutorial, and if you are still not, it's basically binary search. Let me simple say it. Okay. The idea is that using binary search, you can split this whole 2n point into 2 halves. Okay. If they are so maybe if I share my screen. Okay, so you have 2n coins. Okay, and my job is to, so let's call this one set S. I want to do these 2 things. I will split up into S1, S2. Okay, so if the number of fake coins is even, then I will have S1 equals to S2, size of S1 equals to size of S2, and number of fake in S1 is equals to number of fake in S2. Or in other words, I can say that the weight of the S1 is actually the weight of S2. And if they are odd, if number of fake is odd, then what do I do? Then I will want to split the same thing, but I will basically, there exist 2 coins, okay, say called C1 and C2, such that one of them is odd. Okay, so exactly one of C1 and C2 is fake, and the rest of the coin, meaning S1 minus C1 plus C2, this can be written as 2 coins. I can split them into 2 parts, S1, S2, okay, such that size of S1 equals to size of S2 and the weight of coins is weight of S2. Now, if I do this one, then what happens is that in this case, what happens? I know that the number of fake coins is even, that is the last bit is 0, and I have got down another set which is half the size. Okay, and I can continue with that. And here also I will do the same thing. I know that the number of fake coins is odd, and I will have this one which is just, I mean, half the size. And I want to do all of it in just log n weighings. How many of you have got it? Actually, let me ask this following thing. If you have got it, can you just maybe send a quick thing in the chat that yes, yes, or something? None of you have got it?
I think Sajid.
Yes, sir.
Who got it?
Sir, I did this problem in the assignment.
Okay. So you have it. Okay, so
yes.
then you are not the person who are asking a question.
Sir, it was Surjit Appa who was asking.
Oh, okay.
Sir,
Yeah.
sir, in this step that you described, you
Yes.
assume that the mod of S is even, right?
Yeah, so let's think of mod of S is even. Okay. Even
So,
if
but
it is
then-
not. Yeah, that's
so-
why I don't think made of S is even. That's why I'm starting with 2 endpoints, right? Okay, now
right.
what happened otherwise? Yes, you're right. You can. Yeah,
Actually,
to-
so the problem is, even though we may start with an even number of coins, but if it's not
yes,
something
you
like
might
2
not
to the
get
power
it.
n,
Yeah, you're completely right. But that is not, I mean, the reason this 2n was kind of asked, given to you, is just to help you in starting the whole process. Okay.
okay.
Once you do this first part, you realize what has happened basically.
Oh, okay. So then once we realize how to do it in this step, then the generalization would be easier.
Yeah,
If the
basically.
number of coins was odd. Okay.
Right. Okay. So, I mean, this is actually binary search. The way in which I would like to think of it is that think of them as coins. Okay. Let's put the coins in a circle. Okay. And this is a center, say. Okay. Now I want to partition into 2 halves. So I want to partition it into this half. Okay. So 1 half is yes, 1, 2, 3, 4, 6, 1, 2, 3, 4, 6, right? Good. Now, which is 1? So this is say left half, this is right half. So any partition I can think of as how do I want to define the left half, right? I can say that, okay, so let this be the case. Okay. So if I have an arrow pointing like this, then I have this left half and right half. If the arrow is pointing into this other side, then what is left? Which one is left?
Swapped, it will be swapped.
It becomes opposite, right?
Yes.
Left and right. Okay, good. So now let's see what happens in the case of binary search. Okay, so in the case of binary search, what happens is that I have A1 to AN and I am searching for B. You realize that, okay, see, this is bigger than B is bigger than A1 and B is smaller than AN, right? Then what do you know? That means if I am comparing in some sense, say, I'm saying that at this point here, if I measure B with AN, B is lighter. If I measure B with A1 is lighter. So somewhere.
So is it sorted? A1 to
yeah. Let's assume it's sorted. Yeah, it's sorted. Okay. So that means I know that if I just try to change, okay. Actually, you don't even need to be sorted. Okay. So let's say that. Yeah. So okay, let's say it's sorted. Okay. Fine. So that means here, so what happens to the an minus 1 is b. So I want to find, so let us not worry about this particular thing. Okay. So I want to find a place here, ai and ai plus 1, such that b is less than an and more than.
So we do a binary search, right?
We do a binary search, right?
Yes,
So I
sir.
want to just find the place where it kind of, I'm not even wanting to do a, say, let's forget this equality thing, okay? Let's say that I have a string of numbers they want to an. My guarantee is that, with a b1 is b is more than a1 and b is less than an. Now I want to find out a place where the flip happens. I know there exists a flip, right? Correct. Yes. Because here b is small, here b is large. So somewhere or another, if I say, oh, if this is b is small, okay, maybe the next one also b is small, next one is b is small. It cannot continue all throughout, because at some point of time it has to flip, because here b is large. So if I do a binary search, I will be able to find out one place where this flip happens. Correct?
Yes, sir.
Any questions here? Hello?
No questions.
No questions, right? So okay, good. So you are realize that in binary search I can do that, right? Excellent. Okay.
Yes, sir.
Good. So now think of it here. I have these coins. Back to the coin problem. Okay. So say at this time, okay, there's three things possible, right? At this time, I can have that L is equal to R. If L is equal to R, I mean, I'm always talking about weight. Okay. Weight of L is equal to weight of R. Then I've already got a partition. Game over. Right?
Yes.
Yes, sir.
If so, but what happens if L is less than equal to R? Then the important thing is that, so if I call this one as a one direction, what happens if I consider the other direction? If I completely flip this one, meaning I take the elements of the left and putting it into the right.
So then R will be
L.
lesser than or equal to L.
Then R
Okay.
will be less than or equal to L. So in some sense, if I kind of change the direction from this, so slowly to this, at some point of time, somewhere, the flip must happen. Right? So this side, L is, so when it is here, L is less than R. When it is here, L is bigger than R. So there must be a place where L, the flip happens, right? So let's see this flip. Let's say that I can do binary search and find out this place. Okay, so say this is the place. I can do binary search. I binary search and find it out. What does it mean here? That means that right here, okay, so if I take, so there are two things that are possible, right? At this point, I can say that, okay, here, maybe I have already got this left equals to right. So that is also possible, right? So there is a possibility that here, left is equals to right. Then we are done. If not, I know that this is the place where the switch happens. So that means if I draw these two lines, okay, maybe if I draw using a different color, okay, meaning note that the purple left, what do I have here? So I have that purple left is, what happened, less than or equal to purple right, but the orange left is bigger than or equals to orange right. what is the only thing that has changed here between these two?
2 coins.
So 2 coins.
Just these 2 coins, right? So I am just taking this coin and this coin. Think of it, these 2 sides of the balance have same coins. I'm taking 2 coins, I'm switching them, and boom, the balance is going in the opposite direction. What does it mean?
So that means one of them is fake, one of them is real.
One
Because
of
the
them is
weights are
fake, one of
Hello?
them is real, and yes.
Sir, can you kindly explain the criteria when you are choosing the 2 coins again?
So I am finding out a place where the flip happens.
Means
You
it is less than B and another will be greater than B.
Right, that's it. L is less than R, and so here L is less than R, and the next one, in the orange one, L is right greater than R. It is exactly like this. Do you understand?
Yes, sir.
Good. So what do I have if? So if at any point of time I do get L is equals to R, then game over. Game over meaning I can move to the next step. Then I know that, okay, I've got L equals to R. That means the 2 halves have same number of coins and same weight, and therefore the total number of fake coins must be even, and live with that and continue. Okay, fine. If
Yes.
not, I have got these 2 coins, these 2 red coins, and one of them is fake, and more importantly, the rest of the coins here and here, they have the same number of fake coins because they are same weight and same number.
Yeah, okay, sir, got it.
So they must have same weight, because if they had unequal weight, then one of them must be
Correct.
heavier by a multiple of real minus fake, right?
So they have the same number of coins always.
Right.
Note that
right.
left and right always have same number of coins. Okay.
Right.
So if left and right always have the same number of coins, then left is heavier than the right only if and only if the left has more whatever fake coins or less fake coins than the right than the right.
Right. So what if the initial arrow that you chose
Yes.
was one of the yellow or purple lines? Would that not be a complication?
No, what is the problem? So that will be the case when then in this case, this change happens right here. How does it matter? Change can happen anywhere.
So we were going. So let's say we started from the red arrow, and
We started from the red arrow,
and we are going towards the green arrow in some sense. This is the domain that we've restricted ourselves to, right?
Yes.
So and let's suppose that we change our arrow direction clockwise in our search.
We are not changing it clockwise. That's the thing. We are changing in the binary search.
So binary search would mean that we would want to. Okay, firstly we've considered the red.
So
arrow.
let's put it this way: with red, okay. So at this red case, okay. Right. So red L is less than R.
Right.
Okay. Now I can talk about red -1. This one. Let's say dash dash. You can see the dash one. Okay.
Right. So can you also give it a directionality, sir?
Yeah, maybe let me put blue. Okay.
Oh, okay.
So in this blue, I don't know how L is related to R. I have no idea.
Right.
Okay. Then I have the next one also. I have no idea how this one, maybe the particle for now, say. Okay. Right. I don't know how is it related to R. I don't know how orange is related to R.
Right.
Okay. And there's some more. But what I know is that the green, it has flipped.
Right.
You see this?
Yes, sir. Yes. That
okay. So one is less, one is more. What
right.
do I want? I want an I. So let's call this one 1 to n. Okay.
Right.
So I want an I. So I want an I such that, okay, at the ith level, So maybe let me call this one Li just to make our life more simple. Okay. Li is, I wanted to flip. Li is greater than Ri and Li plus 1 is less than or equals to Ri plus 1.
Right.
That's
Which
all
is
I
just
want. Yes, this
right.
This I can find out by binary search.
Right. So can you just go back to the original diagram that you made? So here, the sequence that you're considering is essentially covering the arrow's directionality from in a clockwise direction from red to green.
Yes.
Right?
So this
So
is
that is
n. This is n minus 1, n minus 2, and this is 1 basically.
right. So now, sir, what if I was saying, if we look at the red arrow and we go anti-clockwise in one step. So what if those were the flipping points?
It doesn't matter. What means anti-clockwise? So I
Oh,
know
okay. Because
I know that there exists a place where it will flip. Period.
Okay. Actually, sir, the two arrows which are causing the flip, even the opposite directions of that will also cause the flip.
Excellent. It's excellent.
Right.
Okay. Sir, so only one more doubt. If we were to, let's say, okay, a key part of this argument was the fact that we're using a diameter. So if we were using a sector instead, let's take a.
The key part of it is not diameter or anything. It's just binary search. That's it.
So, but then what we needed to ensure was that by the time we go to the diametrically opposite direction, then we know that there has to be a flip, right?
We know there has to be a flip. Whether you go from the anti-clockwise direction or clockwise direction doesn't matter.
Right. So just let's just say I'm proposing a more general setup, and there is a fault, because if we say instead of, okay, let's think of we are trying to rotate a hemisphere in some sense, sorry, not a hemisphere, a semicircle in this case, right? Because the diameter essentially makes two semicircles, right?
Right.
So we're essentially rotating a semicircle and looking at comparing the two different semicircles. Now, if we were to instead generalize the semicircle to a sector, let's say.
Yeah, you can do that. That's perfectly fine.
So, but then the problem is, if let's say the sector is a quadrant of the circle.
Again, question is that, again, forget all this geometry. Okay. Issue is that, can you guarantee me this? If you can guarantee me this, that's fine. At one end, it is one direction, the other end is other direction.
So actually, I'm trying to go somewhere with this. Why I was proposing this sector argument is, okay, firstly, we can know that if we were to use a quadrant, which is to say that every point that comes under a certain
question
quadrant.
That I'm not very clear. What is the question? Or if the quadrant is the case, what is it that we are trying to do? What is not trying to do? Right.
So okay, I'll go very directly. I'm trying to prove that this construction wouldn't work in terms when there are odd coins. I'm trying to prove that by saying that in that
what
case,
do you do with an odd coin? Think about it. Okay, you can do it. Believe me.
Okay. So would we have to firstly pick out one of the coins or something like that?
Yeah, basically, you pick up one coin, it becomes even to the whole thing, right?
Right.
And now you have a two partition. If it partition into two halves, okay, all you have to find out is that this coin is a
fake or a real one.
Fake or real. And if otherwise, you have to do the same thing. Okay.
So if
just think about it a little bit, that is not the hard part, okay?
Okay.
That is not the hard part at all. Okay. The hard part was, I mean, the only thing here was to use the binary search in a clever way. That was the only thing that was interesting here.
Okay, right.
Okay.
Yes, sir.
Yeah, so somebody has wanted to ask some other question. I hope that I've answered this coin poem. Who was the other person? Who was the person who was asking?
Sir, it was me, but that's also a problem question. So I don't think
that also a problem question, meaning
it's a problem. Like in an M cross N matrix.
I mean, it's a problem that has been given in a.
No,
in
it's not an
assignment?
assignment problem. It's a new problem.
It's okay. If you want, you can ask me.
Okay, so we have an M cross N matrix which is filled with zeros and ones.
Okay. Right.
And we want to find all such submatrices which have all zeros.
Right.
So we want to find an algorithm that counts the number of submatrices which have all zero elements.
What do you mean submatrices?
Like let's say it's 1 to M and 1 to N. So let's say the lower two rows are zero. So
No. Do you really mean submatrices, or do you mean like so there are lots of way of defining submatrices? Okay. So like for example, if I define it 1 1 0 1 1 1 0 1 0, here this row, and so I mean this row, this column also forms a submatrix, which is basically this one. This
no,
one,
I mean they have to be consecutive.
okay. So you want the consecutive things, and you want to find out all of them that are zero.
Yeah, so the answer here will be 4.
Answer will be 4. Okay, fine. Yeah. So you want to solve it.
Yes.
So where did you get this question?
Sir, I was just searching for problems and found this.
Okay. I think this problem will take, you have to wait a little bit more for this thing. Okay. One thing you can try, okay, you can try is basically induction. Okay. And that is actually not hard. You assume that you have an answer, you want to answer for M cross N. I will do it for M minus 1 cross N. Right. In fact, for 1 cross N, I can always answer, right? So assuming that I have an answer for M minus 1 cross N. So what is M minus 1 cross N? M is the number of rows, right? Yeah. So I have the matrix. This is M cross N. I'll take the last row. I'll take it out. Now, if somebody has given me all the submatrices here, then I have to just look at how many submatrices can be there here.
Sir, we need all the locations also, right? We just can't do with the.
You can pass on the location.
I mean, here we just need to output the count. We don't really need the locations.
Okay. I mean.
Yeah, I mean.
But okay, can you do it with the locations? Can you output the
yeah,
number?
I mean, locations is even better, right? But it will be an even more complicated algorithm, which we do not want to find.
Sometimes you want to do a complicated algorithm. Okay, it's not very complicated. It will be something of the order of, yeah, I don't know. You have to write this expression from there. Okay, by looking at the zeros and ones, you have to make a decision. By the way, while I'm thinking of it, there's some more details here. For example, this one, how many? Okay, say. How many all zero things are there?
Sorry, sir, how many? What?
How many all zero submetrics are there?
It's 9.
Ah, good. So in that case, that can be a lot, right? Okay. So because you are counting all of them individually, right? Yeah. So there are different ways. You have to. Yeah, then okay, you can try to solve it by induction. Okay, not induction, by recursive algorithm.
Sir?
Yeah.
I think there is a simple formula that relates the number of such submatrices if we can find a k cross k square such submatrix.
What k cross k?
I obviously haven't done anything properly, but I think we can find a formula if we can find a k cross k such submatrix.
No, yeah, but this will not be just a plain k cross k formula, right? There will be a lot of other details that will kind of come up there. Okay.
No, sir. Then I was saying if we could do that, then we could restrict our search to just some simple base cases.
You
like
can, to simple base cases. Okay, I mean, I think this is a recursive algorithm thing. Okay, you do it with recursive algorithm. Try to solve it using recursive algorithm. Because recursion basically use I mean, let's say that you have an algorithm that can solve it for any I comma j, I cross j. Okay, what can be solved? You can assume something more. Okay, that there is an algorithm that given a matrix I cross j outputs all the locations of all zero matrices. Using that, can you solve it for general M cross N? Or basically, can you use it? You can solve it for I plus 1 cross j. Okay. Now, this is what I would suggest you to do. Then there are other tricks that can be done, but that I think we will come only after our midterm. Yeah.
Can we say something about the minimum time, like the minimum time that requires that such an algorithm would take?
It's very hard to kind of say the minimum price. One, of course, option is that what is the maximum number that can be, right? So if all of them are 0, then what is the number? Okay, and I believe that the number will be of the order of something n factorial or something. So the minimum time will be.
So it will be m plus 1 squared times n plus 1 squared.
No, of course not. Why?
Yeah, I mean, if all are zeros, then we pick any 2 row and any 2 column, and that submatrix will have all zeros. So
okay, you are understand. If the total number of things is n plus 1 times n plus 1 square, mn square. Okay, yeah, I don't know the lower bound. I have to think about it. Okay. Yeah. So did you get this problem just as a fun problem, or is it from some particular chapter or something in a book?
no, it was just a set of problems. So I don't know the difficulty level. I don't know anything.
Yeah.
About
So so there is something called a dynamic programming which you can do. Okay, but again, all of these things, I must say that in many of these cases, the algorithm. Okay, first of all, you have to read the whole matrix, right? Since you have to read the whole matrix, you can always assume that you have to read the whole thing. So the m times n is always an lower bound. Okay, you have to read the whole input. If you don't read the whole input, you'll get the wrong answer. Right. So m times n is the lower bound. Now, can you do it in m times n? That I am not 100% sure whether you can say it. Okay. Yeah. Okay. Any other questions? I think I've.
Sir, I had a small question about.
Sure. Go ahead.
So I was trying to merge k-many sorted arrays. So we can do that using a min heap, I guess.
Yes.
Sir, I was trying to devise a divide and conquer algorithm. So I devised one, but sir, I was finding difficulties to calculate its runtime.
Okay, so I would suggest that you can just you can try it out and try to maybe this one you can discuss in the tutorial. Okay.
Okay. Thank you.
So let's divide this runtime calculation. Okay. Okay. So any other questions? Okay. So if not, let me quickly go to then where we were. Okay. So today I will be starting on this subject of finding the shortest path in a graph between 2 points u and v. Okay, so we will be doing a 3-4 different algorithms on this. So let me see. Okay, so of course, just to recap. Okay, so the length, I mean, you take any graph. Okay, the length of the path is the number of edges in that path. Meaning, if there's a path from u to v, the length of the path is the number of edges. But if there are weights associated to every edge, okay, then the distance can change. Okay, so usually when you have unweighted graph, we can say the distance between any two vertex u and v is the length of the shortest path from u to v. Now, this is something that we have done in class earlier. Can somebody tell me? Maybe I can ask some person's name. Okay, like Sajid Rizvi, are you there?
Yes, sir.
Can you tell us one algorithm using which I can calculate this shortest distance between u to v in an unweighted graph?
Just a second.
Okay, Rajit Goel, are you there? Rajit Goel.
So can we do something like breadth first search?
Yes, we can do something like breadth first search. Okay, so with breadth first search, we can calculate the shortest distance between any two vertices. If that is something that we have done in the question. So, okay, the problem is what is the shortest distance between two vertices, u and v, and the answer is basically breadth first search. So, if you guys have been following what has been done in the last two classes, you realize that to calculate the shortest distance between any two vertex in an unweighted graph, or this, when the distance is basically the number of edges in a path, all you need to do is breadth first search. Is it fine with everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, I mean, I did ask Rajit Goel, who did not answer. So now, is he there or not there?
Yes, sir. I am there. Actually, I was having some problem with the internet, so it was getting on and off.
Okay, fine. So, but are you fine with this thing?
Yes, sir.
Okay.
Sir, actually, I missed some part. So, could you
Okay.
repeat?
I just told that to calculate the shortest distance between two vertices in an unweighted graph, all we need to do is do a BFS from one of the vertex.
To calculate the depth.
Not depth. The
Shortest distance.
Shortest distance between u and v. Sorry?
Sir, actually, I was thinking about it. It is making a little sense, but I'm just thinking, just a minute.
Were you there in last class?
Yes, sir, I was there. I know what is depth first search and breadth first search.
Okay.
Yes, sir, it makes sense. I've understood.
Okay. So doing a breadth first search will help you to calculate this. Okay. But now let's increase the stakes a bit. Okay, make the problems a bit more complicated. Say that each edge has been assigned a number, a real number, and so these numbers can mean a lot of things. So as we have discussed earlier, that graphs can be used to model various real life situations, and the numbers can be used to represent lots and lots of things. Okay, so we are not going to talk about how the numbers are useful to model things, but each edge is assigned a real number, and the length of a path is the sum of the weights of the edges in the path. Okay, so of course, so in some sense, unweighted is basically all the weights have same weight, all the edges have same weight. That's the kind of unweighted you can think of. And of course, the same thing, the shortest distance between two vertices, u and v, is the length of the shortest path from u to v, where shortest path is the shortest number of edges. So here is an example. So I want to find a path from G to A, right? So I can start with this path. So this path goes to E, then C, then B, then A. The total length is 9 plus 5 plus 8 plus 7. I think if you calculate it, you will find that this path is length 29. But there can be shorter paths. For example, you can have this path, right? 9 plus 7 plus 7. Yes. So is this the shortest path?
So no, FDA is shorter.
There is a FDA that is slightly shorter than that, right? If you take this one, G to F, F to D, D to A, then it comes 20. So already you can see one thing that it is not obvious to see immediately by looking at a graph of such a small size also. What is the shortest path, right? And this is exactly what we want to solve. Okay. Good. Now, as I told you that weights can represent many things, right? They can not necessarily represent the traffic in a road. They can represent lots and lots of other things. So which means that the weights can also be negative. There are various times when the weights that we talk about can also be negative. So for example, here, I mean, we have this 3 edges, but all I've done is I've changed this edge, middle edge, from 5 to -5. And now I have a path which is even shorter, which is 9 minus 5 plus 5, which is 9. Okay. So if I have, of course, add negative edges, then the answer makes complete. I mean, we can define it formally and all those things, and everything will go through.
So length of path could also be negative then. Right?
Length of path can also be negative, right? Is there any issue in this kind of definition? Do you guys see any issue?
Sir, an issue can arise if there is a cycle whose total length is negative.
So if there exists a cycle whose sum of the whole edges on the cycle is negative, then there's a problem. For example, here, let's take this one. So we call this a negative cycle. So look at that this in this graph, there is a cycle, negative cycle, G to E to C to G. So basically I can loop around this cycle and my total contribution will be -2, right?
Right.
And I can keep on looping on. So if my goal is to go to A in the shortest cost, what can I do? I can keep on looping around this whole thing for possibly infinite time, and then at some point of time go to A. So the distance between G to A is basically -infinity.
Sir, is that how you define it? I thought in that case we don't even define it because it can be anything from, it can be any integer from the total to -infinity.
Yes, it's the shortest path. Like the shortest path will become -infinity.
Yes.
Right. The minimum over, yeah, you are right that any number can be achieved, and the shortest path will be negative -infinity, right?
Right.
Right. So okay, there are some things that one might ask. What happens if you are, yeah, go ahead.
Could you please explain how that, I mean, what problem occurs again?
Yes.
Negative
So what
weight.
happens? What happens?
Negative total cycle.
Yes. So here there is a total cycle like GEC. The total cycle has length -2, right?
Yes, sir.
So basically, what I can do is that. So tell me a number. Okay. So you say a number which is 150. Okay, negative -150. Is there a path of length -50? Yes, there is. What can I do is I have to take -2 and I repeat it, say, I don't know, 100 times. So total cost of this, so I can go G to E to C, G to E to C, G to E to C 100 times. So total cost that I've incurred till now is -200. And then I take a path to B to A, which is all total is say another +14 or something like that. So total cost of this path, which is basically 100 times around this loop and then go to A, that is less than -150.
But in doing so, aren't we repeating like
Right.
many points?
So we are repeating vertices, right? So so one can define it accordingly. That says, okay, what happens if you are not allowed to repeat any vertex, or you are not allowed to repeat any edge? Okay, so okay, now we are talking. So it's not a regular small path. Okay, we are talking about a path which doesn't repeat a vertex, a path that doesn't repeat an edge, and so on. Of course, we can define it. And once I define it, then things are finite. Okay, because then the total number of paths from G to A becomes finite and we can have a minus A. So by the way, so these things are something that we discuss regularly. Okay, so in the next few classes that we will see, we will be facing with various kind of assumptions. And the reason the assumptions will be required, I will explain it to you when this requirement comes. So one kind of assumption is that there is no negative cycle. Okay. The another kind of assumption is there is no negative weight, and so on. Okay. So and the question is that can you design an algorithm if you have given this property? Of course, if you are given more and more constraints, then that is easier for you to design, right? An algorithm. So we will be looking at all of it. So let me start with today. We will assume both of them, that there is no negative cycle or negative weight. And then what can we do? How can we compute it? Okay. Yeah. So the job is that you have been given a graph with positive edge weights. And so let's say the weight between two vertices, U and so V1 and V2 is weight W of V1, V2. And you want to calculate the shortest path between U to V. Right. So how do you go about it? So let me try to, any ideas about it? So one thing that I kept on telling you from the first class almost is that in algorithms, one thing that you want to really think of is recursive. Okay, this is something that you want to think always. So basically I have a vertex U, a vertex V, and I want to compute the, so there's a huge graph over here. I want to compute the shortest path from U to V. So what we can say is that, okay, let's look at all the edges that goes into V. Okay, there's an edge here, there's an edge here, then there's an edge here, and then there's the edge here. What happens if I compute the shortest path from U to this vertex, shortest path from U to this vertex, shortest path from U to this vertex, and shortest path from U to this vertex, right? So if I have these vertices to be defined as a W1, W2, W3, W4, then I can say that, okay, first of all, what you do is that you compute, I consider this graph G and G minus V. Compute the shortest path between U and W1 in G minus V. Compute the shortest path between U and W2 between G minus V. Compute the shortest path between U and W3 in G minus V, and U and W4 in G minus V. Note that the G minus V has a nice property. What is it? It is at least one vertex smaller than G, right? It's like a typical good thing for induction. Now, once I can compute all of them, then the shortest path between U to V is the minimum over what? W1, W2, W3, W4 of the
distance from U to WI plus the distance from WI to V.
Exactly.
Or the length of the path from WI to V.
Yeah, length of the WI to V, right? Yes. Good. So this is the first thing that always should come to your mind. Okay. Do a recursive algorithm. Let's not worry about the cost and all, time taken and all those things first. But let's see. So recursion is always the first thing that you can think of. Try to solve it for a smaller sized input and then use that knowledge to solve it for a bigger size. Okay. Is it fine?
Yes, sir.
This idea? Okay. So let's see what happens if we do this. Okay. So here we have done that. Okay. So we have this from, so I want to compute the shortest distance from U to V. Okay. So I have, let's, just one second. Yeah, I don't know. Yeah. Consider the short, consider that say W1 to WK are the edges that goes into V. Right, and D of W1 is the distance, minimum distance between U to W1 to WK respectively. And they are in this G minus V. And that's what we just now discussed. So if we do this algorithm, then I mean this is kind of easy to see what we are doing, right? So here is the pseudocode. Okay. So for every vertex W, which is in the, so this is a minus neighbor, meaning the neighbor that from where it is coming, the in neighbors of sorry, this is a mistake. Yeah, so this should be W. Okay, for any yeah, this okay, no, this is fine. Okay, what is it written? Okay, sorry, this should be W. Okay, or in the first line, both of them should be V. All of them should be V. For any vertex V, let's negative neighbor of V be the set of all vertices from which you enter V. Okay, and let's duv be the shortest distance between U and V in this graph G. Then what can you do? You can write that, okay, duv G is basically you compute this d u w for G minus V for all V W in the which are in the in degree of or in neighbor of V plus the weight of V from W. So this is the pseudocode. I have just defined, I mean the same thing that I've written there, right? So now can somebody quickly tell me what is the runtime of this algorithm?
Sir, it's linear in the sum of the edges plus vertices.
Why?
It should
Sir,
be
because this is just BFS and we're doing something before
is
going
this
to the
BFS?
next. Sir,
Okay.
with some added constant time addition steps.
Okay, so let's see how wrong are your intuition in this case. Okay, so this is the correctness of the algorithm. I'm not going to the correctness of the algorithm. I hope that you understand this is correct algorithm. So note that, so let's say that Tn is the, so if the size of G is n, meaning the number of vertices in G is n, let's define Tn to be the time complexity for finding shortest distance between two vertices of size n. So Tn is the complexity finding shortest distance, right? Now, in the worst case, V might have n minus 1 neighbors, right? So I want to, so that will become Tn equals to n minus 1, Tn minus 1.
Sir, this is wrong.
Why wrong?
Because if V has n minus 1 neighbors, then it has the original vertex as a neighbor also. So the distance is just the weight of that.
Okay, so let's say that there, I mean, again, let's say that it is not n minus 1. Okay, fine. N by 100 neighbors. Then what will happen? If V has n by 100 neighbors, then how will you write it?
So actually, even if U and V are both connected, that still doesn't mean that the minimum distance between them is this specific distance, right? We still have to check all the paths.
We still have to check all the paths. That's true.
Because the weight could be quite high for this.
Exactly. That also is true.
Oh, right.
Sir, is it true that we are checking all the DFS, possible DFS spanning trees for this algorithm?
It has nothing to do with DFS as such. No, we are not doing DFS here at all. Okay, we are going to check. This is almost, we are going to check all the possible paths to some level.
Okay, sir. Because what I was thinking is that if V is the leaf of this tree and U is the root, then
Yes.
the limb which goes from U to V in the DFS
Right.
will be a permutation of n minus 1 items.
Yes.
And all possible such arrangements will give us the worst case
Right. So
time
you can think of
complexity.
it that way. You can think of it that way, but not from the DFS tree. It's nothing to do with DFS tree. Right? You are basically looking at all the paths from U to V.
Yes, sir.
Right?
And this comes when the graph is complete.
This comes when the graph is kind of complete. Yeah, you can think of, yeah, graph is complete. Yes, if the graph is complete, you have any permutation will land up there.
Yes, sir, exactly.
Yeah, and then there you will have the n minus 1 factorial.
Sir.
Yeah.
Sir, if we think in terms of let's say we have V, and there are certain vertices which are tables, for example, W1, W2, W1, W2, W3, W4, which lies in G minus V.
Right.
So, so we are checking for the weights of we are checking for weights of W1V, W2V, W3V, etc.
Right.
So now there will be two components here. So another is the DGV part. The G, we have to do the same things for, like, we have to go one step back. Like when we take W1 as V,
right,
and then we will examine some vertices, some edges there. So for so the number of so for every vertices, let's say for V, we examine even number of edges, and if we do that for all the vertices, wouldn't be of the order number of edges into number of vertices, like if we think like that. I mean, am I making sense, sir? I mean, I'm saying,
I didn't exactly follow. See, what is happening, I can tell you the issues. Okay, then now you can try to understand what's going on here. Okay. Okay, so the issue that happens is that, okay, say I have this graph. Okay, I have U. Okay, so maybe there's a lot of other things that are there. I don't know. There's a lot of things. So this is V, this is W1. Okay. Or maybe just forget this one. Okay. W2 and a lot of other things that's there. Okay, so W3 is, sorry, this W2 is also here. W3 is there. So this is the kind of a graph that is there, right? Now, what is the first time? What will I do? I first have distance of U to V in G. So from that, I said, okay, for that I have to give me distance of U to W1 in G minus V. D of U to W2 in G minus V, right? And you go on like that, many other things. Now, when you are trying to solve this, what is it that you can ask? So let's call this one W, say, let's call this one X, okay? Note that from W1, there is a W2 also. So the next step will be form this for this setting. Okay, give me a U to W2 in G minus V minus W1, right? You can also have this other one, G of U comma X to G minus V minus W1. From here also you will have these two things. Say you will have D of U from W1 of G minus V comma W2, right? You can also have G of U comma X from G minus V comma W2. You see what I'm saying, doing? And now let's say, so these are kind of the branches. You can think of these branches are happening, right? Now look at these two vertices. In both of them, W2, there is an edge to X. So one of them will be D of U to X in G minus W1, W2. This also will give you this D of U to X, G of V, G minus V, W1, W2. Note that both of them are same. So in some sense, you are going to call the same subroutine with the same set of values multiple times.
Yes.
Yes, sir. Yes, sir. Yes. We will.
Every time there is a fork in that sense, we would have this, right?
Exactly. So you are unnecessarily, in some sense, doing a lot of computation.
Yes, sir. This will be very.
Sir, I think now we can also increase the computation by, let's say, having a complete graph of vertex 5 and then attaching all the vertices to U and V.
Right. Yeah. So you can see that, I mean, that is actually the main problem of this whole, why are we ending up doing this thing? It's so costly.
Sir, I was thinking of an algorithm that might work better in the average case.
Okay.
So, sir, we start with U, and then, like, based on the weights, we assign probability of moving to each vertex.
Right.
And then, like, we move on, and then we can repeat this process, say, like 10,000 times. And then we can find out like which like the probabilities will be inversely proportional to the weight, so we can like see which paths are like giving us the like the mode of what like whichever is occurring most often might be the path of least like the shortest path.
Wow, I'm really liking your algorithm, I must say. Okay, so this algorithm is actually correct. Okay, the algorithm is actually correct, except that the algorithm, I mean, it's a probabilistic algorithm.
Yes, sir.
Okay, it's a probabilistic algorithm, and it will not necessarily give the correct answer all the time, right? And so to get a kind of an accuracy, you have to run it a few times and all. How many times?
So, but this will be like very less computationally expensive.
Yeah.
Like
so yeah, completely right. It will be. It is basically you do a random walk on this graph. Okay.
Yes.
Now this technique is used in many other contexts. Okay, but not in this particular problem, because this problem has a very simple algorithm.
Sir, I didn't understand the algorithm proposed.
So he was doing he is basically going from he started doing a random walk from a particular vertex. Okay. And the probability he takes a vertex edge is basically inversely proportional to its weight. So if you are a vertex U, then you can take say 5 edges out. Okay, you take that edge out, which is inversely proportional to your weight or something. And the idea is that, I mean, he wants to do this one, and once he reaches V, then he stops and he looks at the path that he has taken. Okay. So, I mean, I'm not going to say that this algorithm is exactly correct, but something similar to this can be done. Okay. But I think this is a bit scope of it is a bit out of this class in some sense.
Sir,
it
this
could be
will
the case
minimize
that
the product of weights.
Yeah, there are some issues.
Right.
You can take care of. You can do that thing also, but instead of
not just that, we could the algorithm, if we even if we run it multiple times, there is a sufficiently positive probability that it will take the same path every time.
That is there also. That is there. That's what so it's a so first of all, to take care of the product of weights, you can do it inversely proportional to not that weight but exponential of the weights. So that what will end up happening is exponential of the sum of the weights. Okay, so I am not. So there are ways of fixing this one. Okay, so this area is what you will possibly learn it more in your MStat program maybe, It's basically called the Markov chain and Monte Carlo method. Okay. It's a probabilistic technique to go do some sums. It is not used in this context, but it is used in other context. But something very similar to this. Okay. So if you guys are interested, you can go and maybe do a little bit of small reading outside this course also.
Oh, sir, also like since Surjitapu pointed out that we would be minimizing the product of weights, I think we can like fix this by taking a log of the weights and something like that.
You can take it fixed, not log, it's exponential of the weights.
Oh, yes, sir.
Yeah. So if you want, you can read this one. So I am not, again, this is not, is a bit of out of the scope of this particular course. Okay. But yeah. But the reason this is not used in this particular context is because this algorithm, there is a very simple algorithm of this. Okay. And the basic idea is that, see, just like we are trying to store this information, right? Why not I store this information, or instead of doing this computations multiple times, why don't I store this information? And this is a very generic technique, which we will see later on also. So let's see. Okay. So we want to reuse the computation. That is the main thing that we can do. Okay. So say I want to start from G. Okay. So the main idea here, okay, here is an algorithm. Okay, and let's see the full, think of the proof of it later on. Okay. So sometimes in algorithms, instead of designing a particular thing, okay, designing an algorithm for a slightly more complicated thing is slightly easier. Okay. So here, what we wanted, so we wanted to find the shortest path. We wanted to find the shortest path from U to V. Instead of that, what I will do is that I will try to find, okay, so it is kind of enough to show if you want to say it, okay, enough to show that find the shortest path from U to any vertex. You might say that, okay, why are you doing this? This is way too complicated. I might not be interested in this thing. But as you can see here, that any vertex is anywhere coming in the picture always, already in this kind of computation, right? Since U to V, W1, U to W2 are kind of coming up. So instead of that, why don't we even try for doing this? Maybe that will help us to do something more nice. So let's see. I want to do this one, okay? So is everybody fine with me? That our job is to compute the shortest path from G to anything. Now, first of all, can you tell me any particular vertex and tell me what is the shortest path? Which is the easiest one to say in some sense?
Sir, E is 9.
E is 9.
E is 9. Why? Because
all out edges from G have weight 11 and 9. So minimum of
minimum of them is 9 E, right? Among the out edges of G, and there cannot be any other path, because any other path will have to use one of the out edges, right? And something, and because we are assuming that there is no negative edge, so there cannot be any other convoluted path to E that is lesser than 9, right? Are you following it? This is exactly where we need the fact that all the edges are positive. Okay, so at this point, I have looked at all the edges that goes out of G. I have looked at the one which is smallest. that is E, and I have sealed it. And okay, now for E, I have got the answer, and there's no way it is changing. Although I have not looked at any other thing, I already know the answer. That is because there cannot be any other convoluted path from G to E. Because to, right? So what is the next? After this, which is the next one? Can you say?
If.
F? Are you sure?
Yeah, I mean, F is just 11 away from G.
Okay, but what happens if there was just an 1 here? From E to F, there was an 1.
Oh, that.
I have not looked at that edge yet. Okay, so what we can do is that now let us try to understand how many, what is the cost of reaching. So I will say, okay, see G and E are two vertices I've reached. So to reach F, the total cost that I will have to incur is 11, right? To reach D, how much will I have to incur? Okay, so my job is to, okay, so this is what I will be doing. Okay, at any point of time, I will have two kind of vertices. I will have one which is the gray vertices, and two that are the red vertices. So the red vertices are those for which the shortest distance from U has been calculated. Okay, so say here this is the gray vertices, and inside this there is there's a U over here, and then there are some edges over here. Okay, and this is maybe a set of all red vertices. Okay, maybe there is some. Now for any other vertex which are outside, I want to compute the shortest distance from U to W that will go along the red edges only, the red vertices, and just one step away. Okay, so for all vertices, actually this would be the gray vertices, compute the shortest distance from G, so from U, that uses only red vertices. See, the idea is that I know that the shortest way to go to the red vertices, that I know. Okay. Now I want to see that, okay, where else can I go? So maybe there is two edges like this. I want to compute what is the shortest distance to go to this particular vertex. So it can be going from here to here, or I can go from here to here, right? So I can compute all of them for all possible such vertices.
Sir, if you can find some gray vertex which has an in neighborhood which is solely within the red region,
yes,
then we know the answer to that. What should be the cost of reaching that vertex?
Yes, if there is not, then they are infinity.
So if there is not, then
we say that this weight, then the cost of that one is currently infinity.
Okay.
Okay, so this is infinity. Okay. So at this time, this will be the cost, right? So this says that, okay. So what is written here? So this says that 10 is written here. This is say 11. This is 12. This is 11. Something like that. So this means that from U, I can see I have to go. right? From U I have to go. Think of it, I don't know, topologically in some sense or geometrically, that I know how to reach all the red points. Now I have to expand one more step. I have to conquer, right? So I don't expect to solve this problem, right? That is not possible because that is too far from me. So the next step for which I would be able to tell you exactly what is the shortest distance are these vertices. Okay.
So,
Fine.
so those are the vertices which have their in neighborhood within red region, or are they the out neighbors of
No,
the
they
red?
have at least one. So they can have at least one neighbor in the red.
Okay, okay. So this is the out neighborhood of.
Yes, they are the out neighborhood of the red vertices.
Okay, so now for this time for the time being we just assign them a cost based on the assumption that their shortest path will be within the red region.
No, not shortest path. I'm asking what is the shortest path for those. I'm not claiming, assuming anything. I'm saying that what is the shortest path from going to you to these vertices that uses only red neighbors. That's it. I'm just looking at those kind of paths.
Okay. So you are not labeling them red just right away.
I'm not labeling them red.
Right. Okay.
Okay. I'm just computing the cost of the distance from you to these vertices through this path.
Right.
Okay. So for example, this is 12. This is the path from here.
Right.
Okay. This is 10. This is possibly a path from here, or maybe a path from here. I don't know which one, but one of them.
Right.
This is 11, the path from here, right?
So basically we are doing a BFS with the condition that the path we are storing is the smallest weight.
Right. In some sense, you can think of. Okay. If you want to think of it in that BFS. Okay. So, but at this point, let's think of it. Okay. So if this is the case of, this is the kind of the graph that you can see. Okay. Which vertex can I say now? I want to now color one vertex red. I want to say that, see, this vertex, I have now know that this vertex cannot be reached in any other way, any other smaller way. This one has 10, this has 11, this has 12, this has 12.
So the minimum one will have to be red.
The minimum one. Why? I claim that this has to be the red. Why?
Because if there was any other vertex, any other gray vertex from which 10 is reachable in shorter time,
yes,
that vertex would be an out neighbor of all the red vertices, so the path length will increase.
Exactly. Yes, so for example, there might be a path like this, right? Which is shorter, but then consider the first time it crosses this red boundary. If this path is less than 10, then this must also be less than 10, right? But this is bigger than 10 because 10 is the minimum. So I can say that the minimum of them will always be, now I must know the shortest distance between you and that vertex. Is this clear or should I repeat it? This is a bit, this is not trivial.
Sir, please repeat it.
Yes.
Sir, you are always considering the red vertices.
Yes.
And you are considering the immediate gray
neighbors. Immediate gray neighbors of the red vertices.
Okay. And then the one which is minimum, because I'm considering just neighbors like one hop away, like one. So the minimum one will definitely have to be red because
right.
Okay, by the logic. Okay. And then we color that red.
Yes, and then continue.
Okay. Also, we avoid repetitions like X cannot come again.
Right. So, yeah. So okay. So maybe to start with, we have some gray vertices, and we will basically color some of them red vertices. The red vertices are the ones for which we know the shortest distance between you to that vertex. This is clear, right? Now,
Okay, sir.
now for every other vertex, all the gray vertex, I want to define the cost. I will store or compute the cost of the shortest path from you to that vertex that uses only red vertices. So for example, if my u, okay, so if I have a vertex v, say, which is a red, yeah, so say w is a gray vertex, okay, I am looking at all the paths we start from u, maybe v1, v2, v3, v4, and then w, or v2, maybe v4, v5, then w. Okay, let's look at all those paths that doesn't use any other gray vertex. It only uses red vertices. Okay, now fine. So let's put this cost of that w. Okay, let's call this one, say, d. Okay, so let d of w be the cost of, or the weight of shortest path from u to w using only red vertices. Is this definition clear? Hello?
Yes, sir.
Yes.
Yeah, the person who asked me to repeat, can you just
Yes, sir. Yes, sir. Up to this, it's fine.
okay, after this is fine, right? Okay, good. So now, okay, among all these w's, okay, so I job is to let, okay, w naught to be the minimum, or argmin to be the vertex with minimum d distance. Okay, do you understand? Fine.
Yes, sir.
Okay, so my claim is that the minimum distance from u to w is d of, or w naught is u2. Now what do I mean by minimum distance here? So minimum distance is not just the distance that uses only red edges, but among all possible paths. All paths. Okay, so this is my claim. Okay. Now, if this is the claim, what will I do is that then I can basically color. So now I know what is that the minimum distance of u to w naught. I color it red and move to the next step. Okay, now why is this claim correct? Is this claim statement fine?
Yes, sir.
Why is this claim correct? So let's say it is not. Okay, so prove. Say contradiction, prove by contradiction. Say that let there be another path, okay, u v1, v2, v maybe 20, and then w naught, that has cost, that has weight less than d of w naught. Okay, strictly less than.
Okay, sir.
Okay, now can that be happen? Note that the first one is red in color, right? U is red in color.
Yes, sir.
This one is black in color, or gray in color, right?
Yes.
So there must be a first time it becomes from red to black.
Yes, sir.
So let's, without loss of generality, let's say that here it is red and the next one is black. Okay.
Okay.
So let's call this one X, and then something happens. Okay. So at that time, that means U, V1, V2 are all red, right?
Yes, sir.
And X is black. So what is the weight of black, red there? What is this one?
So
How big is this?
just d of x only, because we will reach it using red vertices only.
So this must, and because I have taken the minimum, right? So this must be more than d of W naught.
Oh, okay, sir.
Right?
Yes, sir.
Because this I have taken the minimum one, right? And now there are some more steps there. So how can, and they're all positive. So the total
Okay.
length of this path has to be more than d
More
of W
than,
naught.
and we arrive at a contradiction. Okay,
And
sir.
we arrive at a contradiction.
Okay, sir.
Is it clear?
Yes, sir. Yes.
What about everybody else?
Yes, sir.
Okay. So this is basically the main thing. Okay. So here, for example, here after we have colored E, the next thing I would like to color is basically I want to. So if you do this computation, you will see that what happens is the C to be the smallest one, and so on. So actually, I'll try another calculation. I will just show it to you. Okay. So here is it. Okay. So I start with this graph. At this, to start with, G is, I start with G, right? Sorry. Yes, I start with G. G has weight 0 because there's nothing to reach from G. Every other vertices have weight infinity. Okay, so there are two rows. The bottom rows will mean that I have made them red. Top rows is non-red. Okay, so first thing I do is that I make G red. As soon as I make G red, I have to update the values. What is it at this point? Okay, for F, okay, I've added G now, right? So I have to update the weight of F to infinity to 11 and weight of E to 9, right? Now the next thing is that among these things which are right now on the top thing, I look at the one which is smallest weight, which is E, and I put E down. Now, as soon as I make E to be red, then I have to update them. Now, what is it? What is C becomes? Now, C was infinity. Now, if E is 10, I see that, okay, can I reach C from E? Well, yes, I can reach C from E. So it's 1 plus the weight of 10, E, which is 9. So E should be equals to, C should be equals to 10. What about B? Yes, B also I can reach. I can reach from E. So this is 9 plus E is 9. So 18, B is 19. D is, say, here I can reach from E, fine. So 9 plus weight of E is 9. So note that at this point, what it says that I can, this is the amount of places where I can reach D by using only vertex G and E. Now the next thing would be to take this ones 18, 10, and they, so also I'm look at that I have also stored the edge from which I am connected. Like F is currently connected to G. The F smallest thing is achieved through G. D smallest thing achieves through E. C smallest thing is achieved through E. And B smallest path is achieved through E also. So among of these things in the top, I take the minimum of them, which is 10, and put it down. At that point, what happens? Let's see what happens. Okay. See, nothing changes because if I make this C to be 10, right? B could have changed and B had a new way to reach. So what is it? So since B was in the neighbor of C, I go, okay, I can reach from C, and that is 19. Okay, that's not good enough. I updated it, but there's nothing to update because it is still the smallest one is through E. Right? Okay, so that is how we are. So now out of this top 3, I will take one more down. And we have chosen this 11 down, right? Because 11 is smallest. So now once I make 11 down, what all things will change? Maybe I should go back one step. Once I colored 11 red, then I should look at these neighbors of F. So one neighbor of F is E. Now E is already been done, so I don't need to look at it. But another neighbor of level is D. So D at this point has weight 18 because it is coming through E. But now if F becomes red, D can also reach from F, right? So in that case, the cost of path via F would be 6 plus the weight of F, which is 11, which is 17. So in that case, D would cost will be 17 and it to be updated. And this is what happens here. So D gets updated. So D till that time was trying to reach through E, but now it has been reaching through F. At this point, D will be kind of marked. Okay. And this thing A is now marked as 22 because as soon as D happens, D has 2 out neighbors. One of them is B, but B is not changed again. Look at it. B is 9. If B has to reach through D, it will be D 9 plus the cost of D. Cost of D is 17. 9 plus 17, 26. And that's not good. It's much more than 18 that's stored there. So I'm left with A. A has to reach through D, and that's cost 22. At that time, minimum is B, and I push B down. And there's again nothing to change, and I change A. And that's it. The game of the whole thing. So this is what is called the Dijkstra's algorithm. Okay, a very beautiful algorithm. And so basically, this is the pseudocode that you do. Okay, you start with the vertices in the graph. You initialize all the vertices distance to be infinity, and we initialize it by putting the distance of the source vertex to be 0. Okay, and Q is the set of these vertices that is gray in color. So as long as there is some vertex which is gray in color, what do I do? Okay, I pick up the vertex from the gray in color, all the gray vertices which have the smallest distance. I remove that vertex from the set gray. That means I kind of color them red. I have to now update all the other ones. Okay, so what do? I look at all the neighbors of U. All the neighbors of U, I should update it. Earlier, it was getting matched somehow. So this distance of U, V, will be updated. Initially, it was D of V. Now, you can still reach it by going through U plus W of UV. So whichever is smaller, you update it. And that's it. Okay, so here I have not put up I have not stored this D, E, and all of them. So I am not storing the path as such, but I'm storing the minimum distance between U to everything.
So,
is this fine? Yeah.
Initially something to be 0 here, right?
You initialize the source to be 0.
Okay, and then Q should be V minus source, right?
All right, Q should be V minus source. That's true. Correct.
Okay. So I was thinking maybe we can make this more efficient by using a heap. Is there such a concept?
There is. Okay, so I have not told you the cost of the running time of this whole thing. Okay, so let's see what is the running time of this whole thing. Okay, so first of all, at any point of time, I have to find out the minimum, right? I have to find out the vertex from the V, which is the minimum one. So that is linear in time, right? So in the worst case, this can take order V steps. And then I have to update for all neighbors of U, which again might be V of them. So I have ordered V steps here, ordered V steps here. So this while loop cost can be in the worst case ordered V. And now how many times does this whole thing run? Initially, all of them is V, and all of them are in Q, and every time it goes down by 1. So the while loop runs for V number of steps. So total number of, so each round takes order V steps, and there are order V rounds. So total runtime is order V square. Okay, so this is not linear in V plus E, but it is ordered V square. Now, one might say that, okay, can we do something better, as somebody says, that, okay, we are updating this one, we are storing it, can we do this whole process in a much more faster way to a better computation? Yes, you can, okay? So you can look at this book, okay, take any book. So this Dijkstra's algorithm, what we have done so far is certainly there in this course, okay? And try to understand it very carefully. If you cannot understand from my lectures or this video, please read the book and you understand at least this ordered V square step algorithm. Okay. Now the thing that I'm not going to show you or prove to you is that actually there is something called a Fibonacci heap, a bit more complicated version of a heap. It's another data structure. And usually, if you use that Fibonacci heap data structure, then you can reduce this V square to order E plus V log V steps. Now, I am not going to describe you this Fibonacci heap data structure at all in this course. If you are interested, you feel free to go and read it by yourself. It's a data structure. Okay.
So,
yeah.
So what if we try to explain it in this way? Suppose that at some point of time,
yeah,
we have some red region,
right?
And suppose we also have its whole neighborhoods cost already calculated and stored in a heap in the regular sense, in the minimum heap sense. Then what we are going to do is we're going to compute the minimum amongst that heap, which will cost us order 1 because it's already in a heap.
Right.
Then we can label it red, and then we can look at this new member in the red regions, its neighborhood.
Yes.
And then we just need to so when we look at that neighborhood, that would have that could have some intersection with the already existing members in the heap.
Right.
So there are two things that could happen. Some members could get updated with their value.
Yeah.
So in the min heap, that will correspond to bubbling them up or gravitating them down.
But that is where the main problem will be. Just using heap, okay?
Right.
This first step will be done in log n steps, log v steps. But this one, if you want to update v of them or a lot of them, that will cost you more, right? It will cost you d log v kind of stuff.
Right. But then it's already v log v. It's upper bounded by v log v, right?
No, see v log v for 1 round.
Oh, okay. Right.
Okay. So that's why you just a plain heap will not give you much help.
So this will become a v squared log v. Then.
Yes, then this will become v square log v.
Oh, okay.
And we have saved from this one, but not
actually, sir, that one will take order 1 first.
No, it will not take order 1. You will get the smallest one, but you have to remove the smallest one, right? Or the removing will take order v, log v.
So why? Because,
I mean, if you take a mean heap and remove the top element, you have to maintain the heap structure, right?
Oh, okay. Yeah. That will take log v, right?
Yeah.
Yes. Right.
Okay. Yeah. But good that you are thinking in this direction. So yeah. Okay. So is this thing clear? I would really request you guys to go and read this one. Okay, this is possibly the first non-trivial algorithm that we found. Okay, the Dijkstra's algorithm. Please read it from any book that you find. Okay, the proof of correctness is not obvious at all. Okay.
Yes, can you share the slides after that?
Yes, I will share the slides anyways. Okay. Yeah.
Hello.
Yeah.
Sir, can you explain the runtime part again? I
Yes, the runtime part. So this is a, first of all, there is a while loop, right? How big is the while loop? Hello.
Yes, all vertices, sir. Like all.
Yes,
They
so
have got all populated with all vertices.
you have to populate it with all vertices, and you slowly have to go down one by one.
Yes, you are removing one at a time, right?
Yeah. So let's say that they are all connected to start with.
Okay, sir.
Okay. So then this whole thing goes down, right? One by one. So the total while loop runs for V steps. Okay, V rounds. Right. Now inside each round, what happens? You have to find out the minimum from the set of all the Q edges, the minimum. The Q on in the worst case can have V of them. Right. So finding a minimum from a set of V stuffs will take you ordered V. So this statement here will require order V steps.
Yes, sir.
Right. Now, what happened to this step? Okay, what is removal? Okay, removal can take, okay, you can think of it that removal take order V steps or order one step, doesn't matter. Now, what is this one? You have to look at all its neighbors. Now, all its neighbors are, how many neighbors can there be? Okay, maybe V in the worst case. I'm giving you an upper bound, right? And for each neighbor, I have to do this whole process, but this is just a one step, order one step updation, right? One minimum between two things. So that means this whole thing take another order V step. So we have this takes order V steps and this takes order V steps. So all total it takes order V plus order V. This whole thing takes order 2 V steps, or which is same as order V steps, right? And there's a while loop that runs for V rounds. So the total cost is upper bounded by V square. Okay, so the minimum takes order V steps, updating takes order V steps each round. Right? So each round takes order V steps and there are order V rounds. So the total runtime is order V square. Is this clear? Hello?
Yes, sir, this is clear.
Yeah. Okay.
Sir,
yeah.
So can you go back to the algorithm?
Yes.
Sir, for each neighbor, when we are updating the distances.
Yes.
So if there are E edges total, then the number of so this for loop, this should run for minimum of V comma E, right? Like
why? For this a for loop?
Yes, sir.
I mean, it's a neighbor of U, a single vertex. How many neighbors are there? How many neighbors can there be? Hello?
Yes, sir. Yes, sir. I get it. Okay.
Okay.
So the complexity of that heap algorithm will become V times maximum degree times log of V, right?
Yes, maximum degree is there. Yeah.
Right.
Yeah, think out the heap algorithm. How can you do it? Okay. And if you cannot do it, then go and read it and find out why it is not working and how it can be fixed. So just heap will not do it, basically. You need some more structure.
So could you give a hint as to what we want to achieve more than what a heap achieves with that structure? What sort of operation should we?
We want to do this operation, right? We want to do this whole operation. Right? These first two operations can be done in order log phi.
Right.
But this operation need not be done in order log phi.
Oh, okay.
Right? So how do you do this operation in order log phi?
So actually, this operation is taking d log v at the moment. So
Okay,
you're
d
saying,
log v, but d log v in the worst case can be, yeah. So think about it. What happens there?
and
Yeah,
so
this-
what is the complexity that we can achieve for this for loop with the Fibonacci?
Oh, for the Fibonacci, this is v log v, not e log v.
No, sir, I meant that for loop.
Yeah, for the
using
for loop
Fibonacci.
here,
Okay.
the Fibonacci heap will be, so yeah, so it will be order. This whole thing can be achieved. This for loop will be, tell me, it will be d plus log v or something.
D plus log v.
Yes.
Where d is the neighborhood size of
Yes.
v.
Yes.
Sorry, a neighborhood of u.
Yes.
Okay. Okay.
Okay. Okay. Okay, so good. So I think I will stop here today. There is no class on Thursday because it's holiday. So I will post assignment hopefully tonight. Okay, but there will be a tutorial on Tuesday. Oh, sorry, on Friday. So let's see what happens there. Okay, and then yeah, we can take it.
Sir, is this possible that this week we don't have a tutorial session? Because I talked to a few of my friends, and at evening during this festival season, we believe we will not find time to attend the class.
Okay, I mean tutorials is for you guys only. So if you
No,
don't
sir,
want
if
it,
you
that's
can
okay.
just shift it, shift
Yeah,
this
give me a
tutorial.
different slot. You have to tell me a slot and I will communicate it.
Sir, we'll discuss among
Sure.
ourselves and then
Yeah,
we'll
perfect.
shoot a mail to you.
Okay.
Thank you, sir.
Okay.
So the assignment will be due on next Wednesday, right?
Something like that, yeah. 1 week's time you will get.
Sir, and what will be the syllabus for our midterm?
Oh, midterm, everything will be done before the midterm, till before the midterm.
Okay. Thank you.
Okay. Okay.